zone. I'm trying to look at the Wannier function that is in the origin, so there is no exponential factor. It's an integral of the Brillouin zone, so I'm writing it actually as a discretized sum of a psi and k, for which I say for one band I'm just going to choose arbitrary phase factor. Instead of sort of unitary matrix, I'm going to chase only arbitrary phase factors. And let's look at this definition. So I'm actually constructing here a Wannier function by choosing arbitrary phase factors already by myself, and by taking as an arbitrary phase factor the scalar product between a localized orbital, say a Gaussian that looks like the Wannier functions that I want to obtain, and the orbitals itself. You see, this is, well, it's unnormalized, but if I divide it by the modulus of this is just a phase, okay? So what I written here, think at a normalization factor like this, is actually an explicit expression for a Wannier function integral over all the Brillouin zone of the psi k times phases that are just exponential to I something. But you see, once I've done it like this, this is actually a definition for which the original arbitrary random phase of the psi has become irrelevant. Because I can take the psi, I can take on top of the psi a random phase, and I'll have a random phase here, and I have its complex conjugate here, so they cancel out. So this definition of the Wannier function is indifferent to the choice of phases, and in the multiband generalization is indifferent to the choice of unitary matrix. So it's a Wannier function, it's what we call a Poorman Wannier function, that is well defined, it's independent of the phases, and is just dependent of what I chose as a Gaussian. And what this is really my starting point for the localization procedure that puts me really in the right basin of attraction of the minimum. And this is just sort of mathematics on how we make these objects that for the case of one band would become a phase just by dividing it by its norm, actually in the general case a unitary matrix. And this is a typical purification procedure in which you take a matrix that is not unitary and you construct the sort of closest analog of that, that is, you really project this matrix onto the unitary subspace. And this is done by this operation. You take the original matrix times the self-adjoint, you take 1 over the square root of that, you multiply it by the same matrix, and this quantity is unitary, and it's equal to this quantity. And I won't prove it, but in order to prove it, you need to do the singular value decomposition. How is it going? You want to run?
I have one question.
Sure.
See, choosing the Gaussian wave function and falling into the right basin of attraction, whatever you say, is expected, because we know from quantum mechanics that Gaussian function has the minimum uncertainty. In that sense?
No, I wouldn't say that. In the sense that what we have the problem is finding out a pattern of unitary matrices that is smooth everywhere in the Brillouin zone. And basically, by choosing matrices that are a scalar product with localized objects, we obtain something that, because of this invariance, no matter what unitary matrix additional we put here, it will cancel out, because if we have an arbitrary unitary matrix here, there will be an arbitrary self-adjoint here, and they cancel out. So it's a sort of way just to extract a first choice that is smooth. So it has nothing to do with the sort of Gaussian and the quantum mechanics, but it's just got to do with the properties of this object with respect to the unitary transformation. It's just that this object is invariant for unitary transformation. And so this initial choice is one that is automatically sort of smooth.
The other point is, in the previous case, whenever you are looking at the multiple minima problem, and in that case, suppose I end up with some kind of minima and density in which Wannier functions look attractive, but I do not know whether that is right or wrong. So how to validate? Is there in chemistry one-to-one mapping?
Okay, so I mean this is a very good question. So mathematically they are all good because all these objects, will give you the same energy, the same charge density, and so everything. So they are as good as the original block vectors. And so in reality there are two issues. Do these objects look meaningful in sort of the sense we think of these objects? And the overall answer is that they have always looked physical and chemical in all the sort of infinite cases that us and the whole community has looked at. But there is nothing more than a sort of heuristic argument that they look chemically intuitive. There is some interesting argument that relates them mathematically to the polarization and magnetization in a solid. So the Wannier function, it turns out, really represented the classical equivalent of an electron. That is, if you apply an electric field to a solid, the dielectric response of a solid is going to be exactly described by the shifts in the centers of the Wannier function. So the Wannier function looks like classical electrons. You apply an electric fields, they move, and that movement will create a change in the polarization that is the exact change in polarization. Okay, so that's the connection. But in truth, that is true no matter if the Wannier function are well localized, are poorly localized, or are delocalized. It's just that if they are very well localized, it sort of gives us a meaningful definition of a classical electron. But it's all heuristic in some ways. So I think I'll just show you some of these objects, and then we have coffee. And so, I've already hinted at what happens if we take all these infinite states in silicon, you mix them all together, and you obtain in each unit cell 4 covalent bonds. And if instead of looking at silicon, you look at gallium arsenide, you see that the symmetry along the bond is broken, and the covalent bond is shifted towards the more electronegative species. Now, it becomes, I think, even more interesting if you look at an amorphous system like amorphous silicon, and you look at the Wannier functions in amorphous silicon, and then what you see is that there are a lot of Wannier functions that look exactly like the Wannier function in crystalline silicon. So good four-fold coordination there, but occasionally there are Wannier functions that are much less localized and whose center doesn't really sit where it should. And those are the signature of electronic defect in your system. And I'll show you an example later on how we characterize amorphous silicon. Or if instead you take an isolated system like benzene, you obtain exactly what Boyce had obtained 40 years ago. In this case, you see what you obtain are carbon-hydrogen bonds. You obtain carbon-carbon bonds, single sigma bonds, and you obtain for each double bonds these sort of banana orbitals. I'll explain to this in a moment. But you see already there are going to be 6 of these, 6 of these, and 3 of these. There are sort of 30 valence electrons, so 15 orbitals. And so this is actually a case in which the localization function has 2 equivalent minima. One in which there are these banana orbitals, one up and one down, representing the sigma bond, sitting on 3 bonds, and the one rotated by 60 degrees sitting on the other 3 bonds. So there are 2 absolutely equivalent bonds. And actually this banana bonds is something that the chemists didn't like in the 60s, and that's why the Foster-Boyce criterion was actually not very much used, and people preferred Edmiston-Rudeman or other criteria, exactly because the sort of not very sort of satisfactory description from the point of view of chemistry of a double bond, so that in this representation would be 1 banana below and 1 banana above. Okay, 10:30 sharp. Actually, let me do just this slide because then I conclude the Wannier function beta. And this is what exactly I wanted to mention in terms of having sort of a description of the electronic structure of amorphous silicon that is sensitive to what the electrons are doing. And so, as I said, if you calculate the Wannier function in amorphous silicon, you find a lot of them. So the silicon is in light gray, and the Wannier function center is the dark black. You see a lot of Wannier function that looks like covalent bond with center exactly in between silicons. But then there are occasionally Wannier function whose center is not in between two silicons. And so now, for the first time ever, you can actually sort of look at the structure of the system doing pair correlation function of silicon. So what everyone can do, say, even with classical force fields, this is the pair correlation function of silicon. It means if you sit on a silicon atom, the probability of finding a second silicon is 0 in the sort of until you reach the first coordination shell with an integral of 4, and then the second coordination shell, and so on. But you can actually look at a pair correlation function in dark black that is a silicon electron correlation function, that is silicon center of the Wannier function. And you see a lot of the centers of the Wannier function are just at a distance that is in between the distance between the two silicon. If I'm here, the next silicon is here, and the Wannier function is here. But if we enlarge this object, we see that there are a few of those that are actually much closer, and those are the electronic defect states. So this object gives you a sort of immediate way to analyze the electronic structure of amorphous silicon and find out where there are uncoordinated atoms that are truly uncoordinated because there is no bond. And actually it's only by looking at where the electrons sit that you can find out that. And that was done by Pierino Silvestrelli and Michele Farinello and ourselves actually 11 years ago. And Pierino, just after, also applied this same approach to study the structure and the electronic structure of liquid water, looking, you see, at the Wannier functions corresponding, these red are the centers of the Wannier function, to the oxygen-hydrogen bonds and to the lone pair. And a lot has been done in describing the structure of liquids using this Wannier function, and in particular looking at the dielectric response of liquids using this, again, because these red centers of the Wannier functions are going to mathematically tell us what is the dielectric response. Okay, I think we'll stop here. We'll do a 20-minute break, so we have coffee. I'll answer any